Today we'll be talking about the periodic law and the periodic table. This is part 2 of a four topic unit on the periodic law and table. We'll be talking about the nitrogen family, group 15. Throughout this PowerPoint, you'll find out information about this family. And you can see that some of the things that we're going to be seeing and talking about are already listed on this first slide. The assessment criteria that are being tested in regards to the nitrogen family are the following. Understand the bonding and be able to explain the unreactivity of nitrogen. Be able to draw and explain the shape of the ammonia molecule. Know and understand the chemistry of ammonia as a gas and in aqueous solutions. Know the industrial manufacture of ammonia and be able to understand it as an equilibrium process. Know and understand the environmental impact of oxides of nitrogen in the atmosphere and nitrates in soils and water supplies, and be able to evaluate ways of minimizing these environmental impacts. Well, let's go. Nitrogen. Understanding the bonding and be able to explain the unreactivity of nitrogen and group 15 elements. Let's take a look at physical properties. Nitrogen occurs as a diatomic gas and boils at near 175 degrees below 0 Celsius. So at room temperature, it's a gas. Phosphorus, down the group, melts at about 50 degrees Celsius. It has a much greater atomic weight and much stronger intermolecular forces are present. Most group 15 compounds have covalent bonds. Nitrogen can form no more than 4 bonds, but if you look on the periodic table, you'll note that there are d orbitals available for those group 15 elements below nitrogen. It's interesting to note, though, for a group 15 element to form an ion with a stable octet, it has to gain 3 electrons. With this attempt to gain 3 electrons, when a lattice is created, there's a lot of energy released. And you can see the kinds of lattices that will be released from the other side of the periodic table with elements such as lithium and magnesium. Let's take a look at the following video that details nitrogen chemistry and its bonding.
Metal chemistry. So as we move across the periodic table, of course, we're increasing the number of protons and we're increasing the number of electrons. What we are not doing is we are not increasing the number of orbitals. So as you get to carbon, you have as many electrons, i.e. 4, as you have orbitals, and you form these electron-precise compounds. By the time you get to nitrogen in group 15, you've now only got 4 orbitals, but you've got 5 electrons. And that has significant consequences. We're forming compounds that are no longer electron precise, they have an excess of electrons. And there are 2 main consequences of this chemistry. We move from nitrogen down to phosphorus and arsenic. Then you'll see with nitrogen, because nitrogen is small, because those p orbitals can overlap very efficiently, then in the case of nitrogen, what we see is a propensity towards multiple bonds. Multiple bonds is one way of dealing with your extra electrons. The other way, of course, is that you have lots of lone pairs. Compounds with lone pairs are going to function as Lewis bases. So these electron excess compounds with more electrons than orbitals have lone pairs, and where you've got lone pairs, you've got compounds that will function as Lewis bases. And that follows simply from just counting the number of electrons that are present in these systems. Okay, so the consequences of electron cess are either lone pairs and or multiple bonds. You're always going to have lone pairs. Whether or not you get multiple bonds is going to depend on the size of your element. Right, so how do we form multiple bonds in the case of nitrogen? Well, this kind of chemistry is clearly going to be very familiar to you from carbon. So in the case of nitrogen, what have you got? You've got one more electron than carbon, and in many ways the N2 molecule is very similar to an alkyne molecule. In an alkyne molecule you have a triple bond and you have CH bonds or CR bonds on the ends. In an N2 molecule you're going to have a triple bond and you've got lone pairs on the end of the nitrogen molecule. How do you form these lone pairs? Well, if we consider each nitrogen atom to be sp hybridized, then you have a linear sp hybrid pointing along the interatomic axis, and that's going to form a sigma bond. We then have got two p orbitals remaining, and remember those two p orbitals are going to be orthogonal to the interatomic axis, and they're going to be orthogonal, meaning at right angles, to one another. So nitrogen chemistry is quite interesting in the sense that what you get in nitrogen chemistry is every conceivable oxidation state. If we look at nitrogen, we can basically take nitrogen with a less electronegative element. Hydrogen is less electronegative than nitrogen. So formally, if we form a nitrogen-hydrogen bond, when we break it, the pair of electrons goes to the nitrogen, so the nitrogen has a negative oxidation state. If we have three of those hydrogens, then the oxidation state of nitrogen in the ammonia molecule is -3. Now if we go to the opposite extent here, we take a nitrate anion, NO3-. Obviously the charge on that species is 1-. Oxygen, what's the normal oxidation state of oxygen? So we have the oxidation state of nitrogen, and 3 times -2 is equal to -1. So by a bit of trivial algebra, we can see that the oxidation state of nitrogen in the nitrate anion must be +5. And we'll see we get essentially everything in between. The obvious place to start when you're surveying an element is with the elements in its elemental form. And there is only one allotrope of nitrogen, the N2 triply bonded molecule. It's an inert, relatively inert gas. Why is it relatively inert? Well, it's non-polar. If you're going to predict the reactivity of something, you have to look at its polarity. So nitrogen N2 is non-polar. Obviously it's non-polar because the two nitrogen atoms have the same electronegativity. So N2 is a non-polar molecule, and it's triply bonded. Any reactivity of N2 requires us to break a triple bond, a non-polar triple bond, with a bond dissociation energy of +944 kilojoules per mole. That nitrogen-nitrogen bond is the second strongest bond in chemistry.
Now, I am not the best artist in being able to draw and explain the shape of the ammonia molecule, but I've got a video that can do that much better than I. It's very short. At the end of the video, there is a molecular structure table and a format for remembering the structure of a molecule that's created. It would be a benefit for you to copy that down. Let's take a look at that ammonia molecular geometry video.
To find the molecular geometry of NH3, we'll first look at the Lewis structure. We want to visualize those three hydrogens in that lone pair of electrons there spreading out as far away from each other as they can, and that will give NH3 its shape or molecular geometry. And that's going to look like this right here. In essence, those valence shell electron pairs around the hydrogens and then that lone pair of electrons above the nitrogen there are going to repel each other, and that's going to give NH3 its shape. In this case, the shape is trigonal pyramidal, sometimes called trigonal pyramidal. We can also use the AXN notation to determine the molecular geometry of NH3. A, that's the central nitrogen there. X, that's the number of atoms bonded to nitrogen, and we have 3 of those. And n, that's the number of lone pair electrons. We have one lone pair of electrons. So we can either memorize that AX3N is trigonal pyramidal, or, if we're allowed to, we can look it up on a table. So if we go down here, we can find AX3N right here, and that is trigonal pyramidal, and also the bond angles are 109.5 degrees. So that's the molecular geometry for NH3. This is Dr. B, and thanks for watching.
Soluble in water. Once combined with water, it creates an alkaline solution. Nitrogen as a raw material for both fertilizers and bombs and explosives has played a large part in modern human history. Most plants cannot use nitrogen from the air, so they must get nitrogen in a different form. And the most popular way to do that is in a hydrogenated nitrogen-hydrogen mix, ammonia. By using the Haber process, nitrogen obtained from the air is mixed with hydrogen released from natural gas, and they're mixed in a 1:3 ratio. Most of the ammonia produced in this process is used to manufacture fertilizer for crops. And we'll talk about that process in just a minute. The next assessment criteria is to know the industrial manufacture of ammonia and be able to understand it as an equilibrium process. Let's look closely at the following video that describes the history and the process for making ammonia. You'll see here a stick diagram that shows that process. Let's watch the video.
All living things require appropriate nutrients in order to grow, to flourish, and to procreate to ensure the continuity of the species. Nitrogen is one such nutrient, an element that is an important component of photosynthesis and genetic material such as DNA, RNA, and protein. But where does it come from? Nitrogen makes up more than 3/4 of the air we breathe. But in order to be usable to living things, one nitrogen atom must be bonded to 3 hydrogen atoms to form ammonia. In this form, the nitrogen is fixed and is in a form able to carry out its vital roles. But unfortunately, nitrogen atoms in the air prefer to bond with each other, and when 2 nitrogen atoms bond, they form a very strong triple bond. This bond is very difficult to break, and therefore renders the nitrogen in the air useless to living things. Ironically, this abundant element is actually one of the most difficult nutrients to obtain in usable form, and is therefore the most limiting factor in plant growth. For most of human history, the soil's nitrogen supply typically came from animal corpse, dead plants, manure, and guano. Other sources included plant bacteria that replenish the soil's nitrogen, legumes, and even lightning, which provided the intense energy required to break the nitrogen bonds. But in the 19th century, the greatest source of nitrogen, by far, was Chilean saltpeter. At the time, this source, derived from rock deposits containing sodium nitrate, fulfilled well more than half of the world's nitrogen needs. However, the saltpeter supply wasn't expected to last more than another 30 years. More and more people began to acknowledge the diminishing supply of nitrogen, and in September of 1898, Sir William Crookes, president of the British Association for the Advancement of Science, delivered an address at its annual meeting. He spoke to a large audience of chemists, warning that the world was facing starvation since the old ways of agriculture would no longer suffice in meeting the food needs of a growing population. Crookes predicted widespread famine within 2 to 3 decades, since farmland was becoming more and more scarce and the population was growing. Crookes told his audience the solution was nitrogen, since nitrogen fertilizers would make it possible to grow more wheat on less land. This was a matter of having enough to eat. This was a matter of life or death. Crookes' speech became wildly popular across Europe. Scientists began the quest to discover a reliable method for fixing nitrogen with the goal of commercializing it to use in crop fertilizers. Months turned into years as the answer continued to elude the hard-working yet unsuccessful chemists. It wasn't until nearly a decade after Crookes' speech that the possibility of success finally became tangible. One chemist was on the verge of changing the course of history. His name was Fritz Haber. Haber worked in a laboratory in the Technical University of Karlsruhe, Germany. In March 1909, Haber was finally able to produce a cubic centimeter of ammonia in his lab. This was a monumental discovery, for ammonia would serve as the perfect ingredient for the creation of synthetic nitrogen fertilizers. However, successfully combining nitrogen with hydrogen worked in the lab for Haber, but would not adequately work on a commercial scale. After Haber's discovery was announced, Karl Bosch, an engineer at Germany's largest chemical company, BASF, was called upon to solve the technical issues of Haber's lab design. With his ingenious modifications, chemical production of ammonia was initiated in 1913 at the first commercial ammonia factory, built by BASF in Oppau, Germany. The Haber-Bosch process was born. This process did not just help to feed Earth's growing population, it was also responsible for an exponential population boom. The profound impact of the discovery was clearly demonstrated when the president of the Royal Swedish Academy of Sciences presented Haber with the 1918 Nobel Prize in Chemistry. Similarly, Karl Bosch was awarded the Nobel Prize in Chemistry in 1931 for his contributions to the Haber-Bosch process. Despite the grand significance of the Haber-Bosch method for nitrogen fixation, the economy during the years between the two world wars prevented the process from reaching its full potential immediately. However, after World War II, ammonia production and fertilizer use gradually increased. When technical advances led to more economical ammonia-producing facilities in the 1960s, demand began to grow exponentially. Today, global fertilizer use is above 200 million tons per year. Other achievements in agriculture, such as high yield, hardier crop varieties, irrigation, and pesticides, cannot compare to the profound contribution made to agriculture and the world by the Haber-Bosch process. Upon his acceptance of the Nobel Prize in 1970, Norman Borlaug, father of the Green Revolution, conceded that if the high-yielding dwarf wheat and rice varieties are the catalysts that have ignited the Green Revolution, then chemical fertilizer is the fuel that has powered its forward thrust. Vaclav Smil, world-renowned Haber-Bosch expert, confirmed this.
To make the protein. So without large application of fertilizers, no green revolution, no increase in yields, and no possibility to have as many billions of people as we have now. This is why I keep concluding and telling people that they're surprised that this is the most important invention of 20th century or of all times, because everything starts in people as far as we are concerned. And you could not have that many people without having that much food, without having that much fertilizer.
But humanity's reliance on the Haber-Bosch process has had some serious ramifications for the environment. Excess nitrogen runoff into water bodies and into the atmosphere is upsetting nature's balance and are proving toxic to the environment. Dr. James Galloway, biogeochemical professor at the University of Virginia, adds,
the Haber-Bosch process converts into the atmosphere to ammonia, and it is then used as fertilizer. The good news is it's feeding a large percent of the world population. bad news is that much of it is lost to the environment after the food production process. And this is contributing to smog, to acid deposition, to global change, to dead zones in the coast, to stratospheric ozone depletion.
However, solutions to these environmental issues remain elusive, as no substitutes for the Haber-Bosch process are currently available to sustain Earth's ever-growing population. When Crookes initially spoke at the end of the 19th century, the global population was 1.6 billion. It is now approximately 7 billion and growing. This huge population increase comes as a direct result of the Haber-Bosch process, which is responsible for more than 99% of the world's synthetic nitrogen fertilizer production and consequently more than half of the nitrogen added to soil. 2 out of every 5 people around the world are sustained by the increased crop growth that relies on synthetic fertilizer. About half of the nitrogen in each of our bodies originated in a factory that utilizes the Haber-Bosch process. Every single person on Earth has been directly or indirectly affected by it. And as the projected world population is expected to rise over the course of our lifetimes, the Haber-Bosch process is here to stay. With such a powerful impact on the world, the Haber-Bosch process has served as the major turning point in our planet's history, as it has nourished crops and consequently billions of humans on Earth.
Know and understand the environmental impact of oxides of nitrogen in the atmosphere and nitrates in soil and the water supply. We'll talk specifically about nitrates in the soil today. Ammonium nitrate is a primary nitrogen fertilizer. It's produced when ammonia solution reacts with nitric acid. The ammonium nitrate can be crystallized and then it can be placed on the land. The problem is that ammonium nitrate is soluble in water. So when it rains or when water is introduced, the fertilizer dissolves into the soil and provides the plants with nitrogen for growth. Ammonium nitrate contains about 35% by mass of nitrogen. But there is runoff. Runoff is more ammonium nitrate solution that is not absorbed by the land, but that goes into water sources. You can see in the picture below an example of runoff from not just fertilizer, but from untreated sewage, animal wastes, and even atmospheric runoff, and the effect that it has on the water supply. Dead fish, the creation of algae, by the increase of nitrogen in the water supply, providing nutrients. The solubility, as I said, of ammonium nitrate poses the real problem. This runoff creates excess nitrate in the water source. And you saw in the last picture, algae. There are ways to minimize the environmental effects of excess nitrates. The following video, Ecosystems Working with Farmers, describes at least one way to address the issue. You can see in the picture below a graphic of what the video will talk about. The individual white dots are the nitrate ions, and if we can have something in the way between where we are placing fertilizer for the increase of growth of plants and the water source, we can decrease the amount of nitrate ions that make it to the water source as runoff.
Consider this dilemma. In this bag is something we need to feed the world. But when we have too much, it contaminates drinking water, pollutes the air, and kills millions of fish. Hi, I'm Susie Friedman, and I work on Environmental Defense Fund's partnerships with farmers to protect the environment. I'm talking about nitrogen fertilizer. Farmers need it to grow healthy crops. The problem is, it's hard to know how much to use. Plants use nitrogen for fuel, sort of like a tractor uses gas. Now, no farmer would leave the gas pumping without an automatic shutoff. Think of the waste and damage if the tank overflows. But with nitrogen, there's no automatic shutoff. Plants can only absorb so much, and it's hard to get the right amount to just the right place when they need it. The excess runs off, contaminating drinking water, causing algae blooms that kill fish, and even polluting the air and affecting the climate. But with too little fertilizer, we couldn't grow all the food the world needs. What's a farmer to do? We put our minds to it at Environmental Defense Fund, and here's what we're recommending. First, low-cost soil and plant tests give farmers much better information about how much nitrogen their crops need. And second, by putting grasses and trees and wetlands in the right spots, farmers can prevent nitrogen from becoming a big problem. Just listen to what one farmer has to say.
Working with Susie to use just the right amount of fertilizer to feed my crops has been good for my business and good for the environment, too.
So, farmers save money on fertilizer while reducing pollution and feeding the world. Make sense?
Our thanks to the hundreds of thousands of people like you whose donations to EDF make new solutions possible.
Again, questions to start your thinking. I'd like you to think about the Haber process. Remember, it's an equilibrium reaction, and it is also exothermic. Take a look at this question and complete the answers to this question individually and provide it to me when asked.